Okay, off we go. We are recording. Let's see here. So, y'all have all gotten emails from me. I hope and presume, I guess 2 emails from me late last week. Must have been. If you didn't get these emails, check your junk or spam or trash folders. I've had at least 2 students already tell me they didn't get the email, and it turned out it was in their junk, spam, trash, etc. folders. Okay, so anyway, presumably, hopefully you got those emails, you saw the instructions, you watched the organizational recording, and you're aware of the website, etc. I hope you've taken the time to read through all that stuff. I know it's a lot. I am not going to repeat everything I said in that recording. I couldn't possibly. It was over an hour. Right? It's a lot to say. By the way, it's all important. That's why I have to do it. Right? I feel like it all deserves to be said. These are the 2 things that I think deserve to be said even one more time. This is a course about ideas and reasoning. I cannot emphasize this enough. Right, this is not a, memorize the formulas and rehearse the algorithms type of course. It's just not what it is. Which, by the way, of course, what will be the point of that? Especially in today's AI, we have looming AI, capabilities and related consequences, right? Why compete with something that's going to win when it comes to, executing algorithms, for example? So we need to focus on things where y'all can win, things that you can offer that AI cannot do, right? And actually understanding ideas, right? They're not there yet, and I don't think it's going to be happening anytime soon, but who knows? The future is hard to predict. Anyway, this course is about ideas and reasoning. Let's try to focus on that. You're going to notice that in my lectures. You're going to notice it on the exams, right? And so I want y'all to focus on this in your studying, in your doing homework assignments, etc. Obviously, yes, you do have to know formulas. Yes, you do have to be able to execute algorithms. And so, yeah, you are going to have to rehearse those algorithms. Just make sure you realize that's step 1, and that you do have to get to good understanding of the ideas and the ability to reason creatively and practically with those ideas. Okay. Second big thing, again, I cannot emphasize this enough. There's too much material in this class to be able to do it all in class. There are lots of courses, especially high school and prior math courses, where the learning happens in class. And then you go home and they'll give you some homework. And they want you to develop some muscle memory, as it were, with the methods. Sure, yeah, fine. You make you do some homework, but it's all kind of repetition. It's a luxury, right? When your class time to class content ratio is high enough, and you can reasonably do that. We've got too much content to be able to do that, in my opinion, right? So for whatever it's worth, this is how all the class, well, not all, but most of the classes all the math and physics classes that I took in college were of the type that we have here, which is that there's a lot of material to cover, and in class they do, what they can, reasonably, picking and choosing the most important, best use of time and all that. But I did a lot of learning outside of class, and just want to make sure everybody realizes that's going to be necessary in this class as well. Okay, and again, I went on at length about this previously, so I won't do it again. Okay, before I move on to talking about math, does anybody have any questions? Feel free. I like to pause periodically because I talk fast and loud, and it's hard to squeeze a question in, but okay, everybody's good? All right, well, let's do some math. I'm going to start off with an introduction. Why is multivariable calculus important? This is a reasonable question if you're going to take an entire semester course. Why are they making me do this, right? Most of you are probably here for requirements. So I think y'all are already probably sold on this claim that single variable calculus is important. right? And some easy cases to make here. Derivatives, after all, are just about how things change. Well, the world's full of stuff that's changing. Derivatives give us a quantitative tool to describe how things change, right? And again, the world's full of change. In fact, very little is actually constant, right? So, tremendously important, broadly applicable. Little harder to talk about integrals. A lot of people misunderstand integrals and think that integrals are about area under a curve. It's really not the best way to think about integrals. I think importantly, not the best way to think about integrals. Most applications that you will see of integration ultimately are not about area under a curve. Area under a curve is a visualization convenience. That's kind of nice in that sense, right? But most of the time you're computing energy or work or population or, there's some practical, some problem solving real world kind of deal. And the area under a curve is a way to visualize it, I suppose, right? But ultimately an unnecessary, questionable even in a lot of cases, way to visualize it. So, what are integrals and what are we actually computing when we do an integral? And it's my way to think about this. I like to think of it as accumulating quantities. Any quantity where the whole is the sum of the parts in some appropriate sense. And we'll talk more about that later when we get to multivariable integrals. But lots and lots of things have this feature that the whole is the sum of the parts. If you have a loaf of bread and you slice it into slices of bread, and you ask, how much mass is in the loaf? Well, it's the sum of the masses of the slices. The whole is the sum of the parts. Does that make sense? Everybody know what I'm talking about there? Okay. So I claim that all integrals, some sense or another, can be thought of in this way. And the world is chock full of accumulating quantities. So that's why integrals are important. Okay. All right, so again, that's all single variable. Now let's talk about multivariable. After all, we live in a three-dimensional world, not a one-dimensional world. Okay, so a couple of easy examples. Now these are not, why you need to take multivariable calculus. I like these examples as starters. Just to point out how you don't have to go to the high levels to be able to see why. Multivariable calculus is not something that only comes up at highest levels and, super sophisticated stuff. These are a couple of real low-level, easy, low-hanging fruit of examples of where multivariable calculus comes up. So let's think about, for example, the temperature in this room. Right? By the way, we have a thermostat over there, and if anyone gets too cold or too warm or whatever, say the word. So I'm going to point out temperature is a function of position. You give me a position. We'll talk about this point right here, perhaps. At that position, I could put a thermometer. I could read what the temperature says. So you give me a location. I give you a temperature. That's what a function is. Well, the location has three coordinates. Location has an x, a y, and a z, right? X, y, z. So what we have here is a function of three variables, which is a multivariable function. And I could very reasonably say, well, look, if I'm at a particular location and if I start moving in some direction, I could very reasonably ask, okay, well, how fast is temperature changing? And here's the weird thing. It's not going to depend just on how fast I'm moving. It's not just about feet per second or inches per minute or whatever that I move. It's about the direction. How do I account for the angles? Right? So maybe I'm going that way. Right? I'm here and I'm going with that velocity. How do I account for the fact that this is below the horizontal and it's a certain amount counterclockwise from straight ahead? How does that factor into the calculation? Right? This is not a single variable calculus problem. So multivariable calculus, by the way, this is a multivariable calculus problem. We're going to totally address how to do this. It's ultimately not that big a deal. We've got to develop some tools, and we will totally do that. Pretty relatable real-world scenario and it's going to require multivariable calculus. Okay, all right, another example. And again, pretty reasonable, I think. If you have a lump, maybe a rock that you find out in your backyard or what have you, and let's suppose that the density is not constant, and I think y'all have probably seen some examples back in Calc 2 where you compute the mass of something that has a non-constant density. And you do it by, cutting it into slices, right? And then arguing that on each slice, you could talk about the volume of that slice and multiply by the density on that slice. And here's the thing, in all of those examples, they carefully constructed the example so the density would be constant on the slices. In other words, their densities were only a function of one variable. Here, density is a function of all three variables. Right? So in this scenario, if you were to take a slice, density is not constant on that slice. Density varies wildly on that slice. So Calc 2 methods are going to crash and burn. Does that make sense? Right? So we're going to have to figure out some way to generalize. In some, how to do this, we'll figure out some way to kind of make a three-dimensional version of the integrals tools that we used in Calc 1, Calc 2 classes to address this idea that density might depend on all the different variables. And we will 100% do that. It's no problem. It's very doable. And again, very simple, low-level example of something you can do that requires multivariable calculus. Everybody on board? Okay, now, lest you walk away with the impression that multi is only good for little simple stuff, right? That, whatever, who cares? How often does this come up? Let me show you some field-specific examples, right? So there are examples in lots of different fields of study. I'm going to start with economics, no particular reason. Here's some variables. I'm using letters of the alphabet that are often used for economic stuff. By the way, I don't know any economics to speak of, very little. But I know approximately what economic models look like, and this is an example. This is not an actual economic model, but this equation that involves all of these variables, this is kind of how a lot of economic models tend to show up. It's not that I can solve for any one of these necessarily, but there's just a relationship that between the five of them, all of these variables have to satisfy for whatever reason. Okay, so let's suppose we're going to do some business in this economic model. Reasonable question to ask. How fast would the price change if, hypothetically, maybe I knew how fast these other variables were changing? So maybe I can measure how fast these are changing, or maybe I can predict, or maybe I have control over these variables, right? And I can turn the knobs on I can decide to spend more money at a certain rate or whatever. Right? So how does knowledge of these rates of change help me solve for that rate of change? And notice, by the way, P, you can't solve for it. This is a transcendental equation. P appears both outside and inside an exponential. Give up solving for P. So we can't just solve for P and take a derivative. Not going to happen. So, well, there is a method that we're going to learn in this class that will allow us to handle this. Right? And we will be able to solve for dp dt without ever solving for P. And it's a multivariable calculus method. So anyway, for those of you who are econ majors, which I don't think we have a lot of, but welcome if you are. If you ever take an econ class, or if you ever just want to learn some economics, this is an example of where a multivariable is going to be necessary. How we doing? All right. By the way, another thing I like about this example. This is a sort of tip of the iceberg observation that I made previously. We need multivariable calculus because we live in a three-dimensional world. that's just one example where you might end up with multiple variables. The variables might be physical coordinates, location coordinates. That's just one kind of variable that we might be interested in, right? There's a lot of talk out there about how, well, beyond 3 dimensions, you won't need that except for, obscure physics, a string theory, 10-dimensional universe and stuff like that, right? Everyone's seen science fiction movies where they talk about the 4th dimension as this spooky, creepy thing. We're going to be doing math beyond 3 dimensions. And in fact, we've already seen math beyond 3 dimensions. Here we have arguably 6 dimensions because we have, including time, 6 different variables. Each variable represents an axis. Each axis represents a dimension. We're doing 6-dimensional math here. Does that make sense to everybody? And it's a creepy, scary thought. I want to recognize that, right? The idea that we're going to be doing math in 6 dimensions, oh my gosh, but how can I can't visualize that. Am I supposed to be able to draw in 6 dimensions? Absolutely not. No way. You can't do it, I can't do it. I don't believe anyone who says that they can, right? The way we're going to do this is we're going to notice certain patterns that happen in lower dimensional cases like 2 and 3 dimensions. Certain patterns that show up that extend very naturally. And not always, but in a great many cases, what we will understand and draw pictures of in 2 and 3 dimensions, we can do the algebra for it in any dimensions. All right. Pausing again. Questions? Feel free. All right, here's another example. Now, those of you who are engineers, I think we're probably heavily engineers in this class. Probably a few physics majors, if I had to guess. All of those students are perhaps even already, but certainly eventually will be using these equations tons. So these are called Maxwell's equations. This is a version, anyway, of Maxwell's equations. So, what's going on here? Right, it's pretty scary looking. If you're a physics or engineer major, you're going to need to understand lots and lots of stuff about these equations. For example, you're going to have to know what that means. Well, we'll talk about that in this class. You're going to have to know what that is. This is a weird one. It seems to be a differential for an integral, but it's a vector. That's strange, right? I think it's the first time you see something like this. It's a weird thought. Turns out it's actually really natural, and we're going to make sense out of that in this class. And then you also have to understand the constructions, right? So all of this together, what is this construction? What does that mean, and how do I understand it? And likewise, what is this construction? How do I understand it? Right? So we're going to learn all of that. We're going to do much more than that. We're also going to talk about why, not only why is this true, but why should this be true? Why does this actually make sense? Why is this a reasonable thing to write down? Ultimately, I don't like the word obvious, but there is a certain point of view, once you understand these things well enough, that says, well, yeah, I mean, that's just what else would it be? I think it's a great goal for us to aim for, to try to get to that point. Why should this be? Again, not that it is true, but why should it be true? Right? So that's going to be one of our goals. I want you all to develop some intuition for why these kind of critters over here relate to these kind of critters over there. And again, we will do that later in the course. And then finally, all of this will help us understand electric fields better. And again, if you're an engineer, if you're a physics major, you need to have a good sense for electric fields. Not just, again, how to do the formulas, but have a good intuition. What do they tend to look like? How do they tend to behave? And having that intuition is very helpful. So it turns out that when you understand all of this math, well enough, then that will give you better intuitive understanding for electric fields. Okay. How we doing? All right. So pretty important stuff, right? Now, again, we've got the low-hanging fruit of, look how broadly multivariable calculus applies. It applies in pretty simple, relatable scenarios. And then look how deeply it applies. It applies in econ. It applies in sophisticated physics and engineering. And I'm going to show you one more example. It applies in chemistry and physics by way of Schrödinger's equation. So this is one of the big equations of quantum mechanics. And if you're a physics major, you'll definitely take some quantum mechanics classes. If you're an engineer, you will need to know a few things about quantum mechanics. And I don't know what course they will do that in, but they will talk about a little bit of probably. Do y'all have to take, the engineers in the class, do you have to take solid state at some point? Maybe? I'm not sure. Anyway, I would imagine you'll do some quantum mechanics at some point. For the chemists in the class, obviously you have to understand molecular bonds. Molecular bonds come from how electrons behave, and electrons behave as required by Schrödinger's equation. So now, good news, we're not going to talk about Schrödinger's equation in this class. Certainly not going to solve Schrödinger's equation, but we are going to talk about this character right here. This is called the Laplace operator, and this is an object of multivariable calculus. So if you want to be able to, in whatever context and for whatever reason, if you want to be able to do some quantum mechanics, you have to know multivariable calculus for that purpose as well. Okay. All right. So to wrap it up, this is the tip of the iceberg, right? I like to say it like this. Multivariable calculus is the calculus of the real world. Single variable calculus is a nice little starter exercise, right? And it is useful, very useful. And ultimately, the way we're going to solve some of these multivariable calculus problems is to turn them into single variable calculus problems, in a way. But multivariable calculus is the calculus of the real world. It's just how it tends to break down. So I hope that's persuasive. Why do you need to know multivariable calculus? Well, because we live in the real world and calculus is useful, and that's what multivariable calculus is. Okay. Does everybody buy it? Okay, so let's dive into the regular part of the class. Procedural point that I want to start with is this comment right here. As we go through the notes, these lecture notes. By the way, these are downloadable on the class website in the class materials folder. You can have all my notes. There will be some stuff that's indicated by this sort of gray shaded box, this kind of thing, where there will be this comment, for students to read. Won't be covered in class. And this is, I'm going to say, represents sort of a compromise scenario between two relative extremes. I talked about this previously, but again, so much material. I can't talk about all of it. Too much stuff. I have to pick and choose. I have to make tough choices. And there are some things that I'm pretty comfortable not talking about in class. Y'all can read through certain kinds of examples. Y'all can wade through algebra on your own. Some of y'all are probably better at algebra than I am, right? So that's fine. Yeah, that you can do. There are some things that I absolutely have to talk about in class, either very important or very challenging or very visual in ways that benefit dramatically from being in person. There's some obvious yeses and there's some obvious nos. The stuff that's kind of borderline in between. I would like to be able to help. In many cases, I don't have time to talk about it in class, but I still want to help, right? And so putting these comments in the notes is, well, y'all can read this. I hope this is helpful. I hope this, makes it easier to read through the book. But that said, we just aren't going to have time to do it in class. class. So these sort of compromise topics that are in the notes, this is why I'm not going to be talking about them mostly. So anyway, whenever you see this comment up here, whenever you see for students to read, that means that you're still responsible for it, right? It's something you have to learn. It's something that you should read in the book and possibly in addition to reading what I write about it. This is just intended to help. Okay. All right. Usually in such cases, I will still say a couple of words. So here's what I want to talk about here. I do want to talk about this notation for representing that vector. The book, lots of books prefer to write it like that. So between these two options, I have a pretty strong preference for this one. And I just want to make sure everybody sees why. Recall that a point, like P1 here, can be thought of as a vector because of the usual sort of one-to-one relation between points and vectors. If you give me a point, I can make an arrow that comes out of the origin. And if you give me a vector, I can translate it to where the tail is at the origin, and that gives me a point, right? So there's this one-to-one correspondence. And points can be thought of as vectors. Vectors can be thought of as points. They're different things. Don't get me wrong. A vector is not the same thing as a point, but there is this very convenient sort of correspondence that when you blur that distinction can be really convenient in a lot of cases. And that will come up lots in this course. So if you think of P1 as a vector, not a point, and if you think of P2, that point, if you think of that as a vector, not a point, then check it out. This green notation all of a sudden just makes loads of sense. I mean, purple plus green is P2, is the blue, right? Purple plus green is blue. So this is a natural notation because this recognizes that. This is the thing that when you add it to P1 gives P2. Okay, so that's why this is at least on the table. Now, why do I have a preference between these two options? Why do I prefer this one? And the short answer there is because algebra is a good thing. Algebra is our friend. Algebra helps us solve problems. This preferred notation that I like better shows the algebra. Why would I want to hide the good stuff? Right? I don't see the advantage, right? I think this is a good thing. When you have a good thing, you want it to be as visible as possible. All right. So anyway, heads up, I will be using this notation, but you will also see that notation here and there. Everybody good? Okay. All right. Real quick. X comma Y comma Z. Got to give it a name. A pretty standard, certainly very common, a borderline standard choice is to call it R. There is a downside to calling it R. We're going to encounter that downside when we start talking about coordinate systems, which will be later. Well, it's the end of chapter 1. We might get to it early next week. Anyway, at that time, we will see there's kind of a disadvantage to calling this vector R. So in order to avoid that disadvantage, for many years, I called that vector the X vector, motivated by the first coordinate being X. It's just a label, right? Seems like a reasonable label. Anyway, that said, you will therefore encounter from like old midterm exams and stuff that I'll have this, X vector, and that's just a reference to what this semester we are calling R. This semester and the last several semesters I've called it R. All right. Okay, so moving along. By the way, we're now officially done with section 1.1. Just a real quick procedural thing. Let's see. The web page, y'all will remember I pitched this thing called the class schedule, and we're going to be using the class schedule a lot. Today, right here, the sections assigned, TBD as of when this was written, but now that we have finished section 1.1, when class is over, I will be filling in 1.1 right here, thus making 1.1 part of homework number 1. Not all of homework number 1, right? Homework number 1 also includes whatever we do here, namely Wednesday. And all of this together, what's in both of these boxes, will make up homework number 1, which will be due Sunday. Does that make sense? Alrighty. Okay, so into 1.2, let's talk about this thing called a parameterization. A parameterization ultimately is a function. I think it's good to start with a crisp, simple, that's ultimately what it is. It's a function. Now, it's a special kind of function, but let's not lose sight of the fact it's a function. So specifically, a parameterization is a function that gives rectangular coordinate position as a function of, I'm going to say, time. It doesn't have to be time, but it turns out it's usually pretty convenient to think of that input parameter as being time. Technically, it can be any single parameter when you're talking about a parametric curve. So anyway, that's all it is. Position is a function of time. Y'all have probably seen something kind of like this before. Calc 1. Bob's driving in a car along a road and his speed is given by the following formula, right? And then you're supposed to integrate that and compute where he is. In particular, the question there is to figure out what is his position, how far has he gone along the road, position as a function of time. Right? So that's technically a parameterization in a way. This is different only in the sense that here we're talking about position perhaps in 2-dimensional space, maybe 3-dimensional space. So for example, here is a parameterization. Let's look at this example right here. This, you'll notice, as required, gives position, x and y, rectangular position, as a function of a single parameter time. Okay. All right, now specifically, there's the function that tells me my x-coordinate as a function of time, and here is the formula that tells you my y-coordinate as a function of time. That makes this now a specific parametric curve and a reasonable question to ask, which is, but what is this? What does that look like? What curve does this parameterize? Okay, how do you do these? If given a parameterization, how do I figure out what the curve is? Well, there's several different things that you can do. We get lucky with this one. With this one, keep in mind, we've already said that is my formula for x, and this is my formula for y. Cosine t and sine t, and I remember, y'all probably do too, an easy relationship between sine and cosine, and that is the sum of the squares is 1, right? It's Pythagorean identity. So, this is always true for these formulas, right? Said differently, if you take these formulas and you stick them in here, this equation always works. And what that means is these positions that are produced by this parameterization, all of the positions that are produced here, all of the output points, they all are on the unit circle. So this parametric curve is just tracing out the unit circle. Does that make sense? What do you have? Now I'm going to say we got lucky on this one. We got super lucky because we just happened to have the Pythagorean identity was just there. What luck, right? You won't always get that lucky. But when you do get lucky, score. Okay. All right, now let's take one where it's not as much of a freebie. Let's look at this. Well, let me do it like this. Let's look at this parameterization. By the way, easy to forget. Don't forget the parameterization is telling you position, right? So this is telling you position, and that means that your first coordinate is x and your second coordinate is y. Is that cool? All right, so here's the trick on this second method. It's a real cute trick. What you do is you solve for t in the first equation. Right, this first equation says x equals t minus 1. Solve for t. You get this. Solve for t in the first equation and then plug that in to the second equation. Right? So keeping in mind the second equation is y equals 3t plus 4. So here it is. That is that second equation. That's exactly what that says. Y equals 3t plus 4. Take what you got for t solving in the first equation, plug it into the second equation. And see, all I did is I took t equals x plus 1, plug that right on in there. And when you do that, all together, check out what we've got. What I've got, let's see here. I've got is that y is that, which is this. So pretty nice how this has worked out. I started out with a parameterization that I didn't know what it was, some parametric curve, and what I see now is that every one of these points satisfies this equation, which I recognize because this is old news, right? Middle school algebra. This is the equation of a line. Everybody happy? All right, now here's a different way to do it. Different solution to the same problem. Keeping in mind, this is our x and this is our y. So here's my formula for x. Here's my formula for y, and as I have indicated here, I see kind of a easy relationship between those, in the sense that they're both polynomials of t. They're kind of similar in that way, right? Not only are they both polynomials, they're both degree 1 polynomials. More to the point, there's an easy set of operations that I can apply to the green formula to get the blue formula. Well, okay, right, but I mean, when you do something to one side of the equation, you do it to both sides of the equation. Said differently, I can manipulate the formula for x to find then a relationship to y. And notice I get the exact same relationship. Right, just kind of fiddling around with that formula for x until it kind of turns into the formula for y. You get the same equation of the line. Is that cool? All right. Okay, so now I have at this point shown you all 3 different methods. Oh, let me get into full screen mode. There we go. 3 different methods for 3 different kinds of scenarios for how to parameterize a curve. There's the get lucky method. It's out there. I mean, you know, take the wins when you get them. So sometimes you get lucky. Sometimes you solve for t in one equation and plug it into the other equation. And sometimes you manipulate one formula to turn into the other formula. So 3 different methods. Why did I show you 3 different methods? And the answer is that none of these methods can be counted on to always work. They just don't. Obviously, sometimes we just won't get some free, obvious, immediate lucky break answer. Sometimes you can't solve for t. I read this stuff one to be super easy to solve for t, but you can't always solve for t. What if this was a cubic expression in t? You can't solve for it. Sometimes there's not an obvious way to manipulate one expression to turn it into the other. Sometimes they're just totally different. So these different tools apply in different scenarios. And I think it's useful to be prepared for anything. So my favorite metaphor along these lines is I think everyone should think of themselves as having an intellectual toolbox. And you collect tools for your intellectual toolbox, and they're useful when they're useful. When are they going to be useful? I don't know. It depends on what you're building. If you're building a shelf out of wood, saw might be handy. Who knows, right? But you might also need a hammer. You might also need a screwdriver. It's just good to have all the tools, and then depending on what you're building, you pick the tools that are useful for that job. Does that make sense? So please don't make the mistake of thinking of this as a, pick your favorite and ignore the other two. This is not what that is. You need all three of these because you never know what the scenario is going to be. Okay. All right. Okay, three-dimensional problem. Here's a three-dimensional parameterization. You can tell it's three-dimensional because we have x, y, and z describing the position. We can't reasonably expect an equation to work here. In the previous cases, we identified an equation that related to what we were looking at, and the equation was ultimately kind of the answer. But an equation, we will soon see, an equation in 3 dimensions typically gives you a surface, not a curve. We know this is a curve because its position is a function of time. We're literally tracing out a curve. So this is a mismatch of type, right? There's no way that something that typically describes a surface could be expected to help us understand a curve. So what to do? Again, tools for a toolbox. Sometimes you will notice part of what you're looking at is familiar. This happens more often than you might expect. The world is full of circles, for example. Right? So, it's not at all rare for a situation like this to come up where, ignoring the z-coordinate, I look just at the x and the y, and I recognize that, right? We studied that previously. That's this thing right here, and we know it's a circle. So that actually is a really useful observation here, keeping in mind that what we've done is to kind of ignore the z, right? If you think about it, ignoring z means wherever you might happen to be, you're just kind of projecting down into the xy plane, keeping only the x and the y, in some sense. So what that means is, just because of this little observation that, cosine and sine, hey, I know how those work. What I know is that my curve, whatever this curve is, when I project down into the xy plane, what I get is a circle. Let me draw the circle down here. I get a circle going around like this. Right now, I haven't even done any algebra yet. All I've done is make the observation that, I recognize that. I've interpreted that as a projection, and so my curve has this shadow in the xy plane. What do you think? Is everybody buying that? Everybody happy? Okay. All right. Related, we can isolate and look just at the z-coordinate. Let's forget about x and y. Let's look just at that z-coordinate. That's pretty easy, right? What happens as time passes? What happens as t increases? Well, z is t. So what happens as time passes, what happens as t increases is that z increases. So taking these two geometric observations, I know that the shadow in the xy plane is doing like this, I know that the z-coordinate is just increasing. Use your geometric intuition. Something whose shadow is doing this and whose z-coordinate is increasing like that, that's going to be, it's going to be like this curve here. And that's what we call a helix. Everybody see what happened there? So we never really quite did the algebra, what that even would be. I mean, we didn't sort of algebraically conclude this to be a helix. We kind of saw it from a couple of different angles and pieced it together. And sometimes that's what you have to do in this nice example of that. Everybody okay? All right. Okay. Again, another tool for your toolbox. Okay, sometimes you got to go the other way. All the examples we saw previously, I gave you the parameterization, and the question is, what does that look like? So, very often, and arguably more often, when you're, going through some sort of, doing some sort of an application, some sort of real-world application, the real world tends not to just give you freebie parameterizations, right? Most of the time you have to make your own parameterizations. Most of the time, you're going to kind of, in some sense, know the curve. And the question is, you want to figure out how do you parameterize? How do you create the parameterization, right? So I think this is an underappreciated problem. The book doesn't really spend much time going into this. And again, I'm just telling you, when I was an undergrad, I was going through taking a lot of physics classes and stuff. I had to make my own parameterizations most of the time, right? So how to do it. This is my favorite method. Again, there's multiple little tricks for this, and we will talk about others later on. But if you have a graph, a lot to say about what a graph is. We'll talk about that later. But here, all I'm going to say is if you've solved for one of the variables as a function of the other, that's what makes this a graph. If you have a graph, it's a really simple little trick. The simple little trick is this right here. Just let t be your input variable. Whatever is the input variable for the function whose graph you're looking at, let that be t. And you just kind of automatically win. It's the simplest little algorithmic trick ever. It's totally awesome. Just identify that you have a graph. What is the corresponding input variable? Call that t and spike the football. Let's see an example. Let's look at this curve right here. Check it out. That's a graph. Right? I've solved for y. Y is a function of x. The input variable that I'm supposed to let equal to t is x, just like it was here. I'm going to do as told. I'm going to let t be that input variable. Here we go. I'm going to let t be the input variable. Input variable is x. I'm going to let that be t. And I claim it's kind of all over but the shouting. We can't lose at this point. Our hand is forced. We're forced into winning. All right? As you'll notice here, because if x is t, I kind of have to make y t squared. And sure enough, I have a parameterization. I have position as a function of time. How you doing? Is everybody all right? Isn't that easy? What an easy little method. Here's a couple of variations of it. Now, you might look at this and say that's not a graph. Quibble. Doesn't look like a graph. But I can rewrite it by solving for x, at which point I see that, in fact, yes, it absolutely is a graph because I've solved for x as a function of the other variable, y. So here, this is a graph in that sense. It's backwards maybe from what you're accustomed to, but whatever. But it's a graph. The input variable is y. Following the rule, I'm going to let t be my input variable. And again, it's all over but the celebration, because look, if y is equal to t, then x kind of has to be that. And again, victory. We've got position as a function of t. Yeah? Last little twist. You might have a different coordinate system. We're going to talk later about this thing called polar coordinates. If you've never seen polar before, it's just this picture where you describe position with an angle and a air quotes distance. I'll explain the air quotes later. But anyway, r and theta are just this picture that gives rise to this. And again, if you have a graph, so for example, this equation right here, r is theta squared. That's not a rectangular equation. This is an equation relating polar coordinates. But it's what we call a polar graph, because one of the variables is a function of the others. And just plug it in. And again, victory. Position, rectangular position, keep in mind. If you're going to talk about a parameterization means rectangular position as a function of a single parameter. Again, victory. So you don't even have to know what this curve looks like to parameterize it. And I'll point out, same thing here. It's really hard to think about what this curve even looks like. And we've parameterized it. Okay, and we're out of time, so we will draw the line right here. Pick up here on Wednesday. Y'all have a good rest of your day. See you later. Look forward to working with you in this class. Oh, really?